There is a hidden cosmic ruler, about 490 million light-years long. It is a fossil from sound waves in the newborn universe. That ruler still echoes inside galaxy maps we build today. Immediate takeaway: sizes in space follow rules set by physics. Gravity stretches some patterns, pressure erases others, expansion times everything. Let me show how the universe decides what grows and what fades. Space once inflated faster than light, blowing microscopic ripples to megascales. Those ripples are labeled by size, called the power spectrum. It is simply a chart of bump strength versus scale. You care because bump strengths decide what structures can grow. Inflation stretches quantum jitters enormously, freezing them as classical patterns. The pattern is nearly even across scales, with a gentle tilt. That tilt favors slightly larger waves and suppresses tiny ones. Phases are random, so no preferred locations, only preferred sizes. During inflation, each wave exits the horizon and stops oscillating. Later it re-enters and gravity resumes the tug of war. Larger waves exit earlier, so they freeze earlier and grow longer. Smaller waves exit later, entering hotter, denser plasma with pressure. Example in real terms: satellites map the microwave sky's tiny temperature bumps. Planck measured the tilt as 0.965. That number means slightly more power on big scales than small. The map speckle pattern is the blueprint for today's cosmic web. From that blueprint, gravity chooses winners and pressure sets limits. Crucially, the spectrum is smooth, so later physics adds features. It sets the stage, then baryons and dark matter do choreography. Net result: we expect structure across scales, with subtle preferences. Picture a spherical wave racing outward through a glowing, early plasma. That wave is sound, pushed by radiation pressure against gravity. Its maximum reach before stalling is called the sound horizon. You should care because that distance becomes a cosmic ruler. Photons drag baryons outward, while dark matter sits in growing wells. The wave travels at about light speed divided by square root 3. Eventually, the universe cools and neutral atoms form, freeing light. The pressure vanishes, the sound stalls, and baryons fall inward. A faint shell remains, roughly 150 megaparsecs across. That is about 490 million light-years in real units. Galaxies prefer that separation slightly, leaving a subtle bump in pairs. Surveys measure this bump and use it to map expansion. Example in real terms: we see the bump near 150. It appears in the Sloan survey and in many modern catalogs. Because that scale is fixed early, it anchors distance measures. We call it a standard ruler, precise and powerful. Change the early plasma and this ruler length would shift. So the stakes are huge for cosmology and new physics searches. Bottom line: a sound wave's last gasp drew a universal tick mark. Find that tick in galaxy maps and you can read expansion. That is how a faint pressure wave sets a scale. A gas cloud listens to gravity, but pressure argues back loudly. The tipping point distance is called the gene's length. It decides which clumps collapse and which get smoothed out. Gravity wins when the cloud is bigger than this critical scale. Pressure wins when it is smaller and waves carry support. The scale depends on sound speed and the background density. Higher temperature means faster sound and a larger protective length. Colder gas shrinks that barrier, letting small clumps collapse earlier. Dark matter adds another twist, called the free streaming length. Fast particles cruise out of small wells, erasing tiny features. Slow, cold particles stay bound, preserving structure to tiny masses. Warm dark matter would wipe out dwarf scales, around 100 kiloparsecs. Cold candidates allow microhalos as small as Earth's mass. That is 24 orders smaller than a Milky Way halo. Example in real terms: dwarf galaxies vanish in warm scenarios, but star streams around our galaxy hint at many small perturbers. Those streams suggest abundant subhalos, favoring cold dark matter. Rule of thumb: pressure and particle speeds set the minimum building block. Net result: there is a smallest meaningful lump, defined by physics. Everything smaller gets washed out, long before galaxies start forming. That floor scale ripples up the hierarchy, shaping later structures. In the hot plasma, photons bounce like frantic pinballs between electrons. Each bounce drags baryons, creating a sticky, viscous fluid. This stickiness erases small ripples, a process called diffusion damping. It matters because it sets a ceiling on fine structure. Photons random walk out of overdense regions, taking heat with them. Baryons cool locally, pressure drops, and tiny waves die out. The typical distance a photon wanders is the diffusion length. Ripples smaller than that length get smeared into near silence. On the sky, this shows up as a damping tail. Power drops at small angular scales, beyond multipole 1000. Example in real terms, Planck sees crisp peaks, then a soft fade. That fade is photon diffusion quietly erasing tiny imprints. In 3 dimensions, it smooths baryons on dwarf galaxy scales. Dark matter resists this erasure because it barely feels radiation. So baryons lag behind, then later fall into dark matter wells. Tiny tests erase smaller waves and galaxies look puffier and delayed. Astronomers use that puffiness to constrain the early plasma conditions. Bottom line, diffusion sets a smallest brush the universe can paint with. Everything finer than that brushstroke fades before structure really grows. That ceiling partners with the floor from dark matter streaming. Together, they define the usable range for early building blocks. Now the scaffolding forms, filaments stretching between nodal clusters. Gravity amplifies overdensities, while the universe keeps expanding relentlessly. Growth rate means how fast clumps get denser with time. You care because growth timing sets the sizes that can assemble. During matter domination, growth is brisk, roughly proportional to scale factor. Then dark energy rises, and growth slows dramatically after redshift 1. Big structures stall first because they need long, coherent infall times. Smaller structures can still assemble if cooling and feedback allow. Mechanically, filaments feed halos, while sheets collapse into thinner threads. Tidal fields steer matter, aligning spins and setting merger angles. Example in real terms, clusters reach 10 to the power of 15 suns. Filaments span tens of megaparsecs, feeding clusters over billions of years. After redshift 1, new massive clusters become rarer in the census. We read that slowdown as evidence for a cosmological constant today. Rule of thumb, growth loves matter eras and hates dark energy. So the picture is, expansion sets deadlines for structure to finish. Miss the deadline, and some planned giants never fully assemble. Galaxies remember those deadlines in their ages and morphologies. Bottom line, the clock of expansion chooses winners on large scales. Measure growth precisely, and you test gravity across cosmic distances. That test ties structure sizes directly to cosmic acceleration history. A dark halo forms, then hot gas tries to radiate its heat. Cooling time versus free fall time decides whether stars appear. This sets a sweet spot in halo mass for bright galaxies. You care because that spot explains Milky Way-sized systems. At low masses, supernovae push gas out, quenching further growth. At high masses, gas shocks, heats up, and cools very slowly. Active black holes stir halos, keeping hot atmospheres from collapsing quickly. Between these extremes, gas can cool and disks can form stars. Mechanically, virial temperature scales with halo mass and radius. Atomic cooling turns on near 10,000 Kelvin, enabling efficient collapse. Example in real terms, star formation peaks near 10 to the power of 12 solar masses. The Milky Way sits close to that favored scale, by luck. Dwarfs lose gas after bursts, leaving metal-poor, diffuse systems behind. Giant halos host quenched galaxies, bathed in hot, buoyant atmospheres. Tiny test, compare rotation speeds across masses and see the break. Feedback creates that break by pumping energy into shallow wells. Above a threshold, cooling fails and gravity hoards a hot halo. Net result, a predictable mass window breeds the brightest galaxies. Outside that window, star formation is starved or snuffed. That window, in turn, imprints a characteristic scale on populations. Bottom line, baryon physics sculpts sizes, not just gravity alone. Pan the camera across a supercluster, then sink into a yawning void. Environment means how crowded your cosmic neighborhood is. It matters because tides and density shift what structures can survive. In clusters, strong tides strip satellites and heat intruder gas. In voids, low density slows growth, leaving fluffier, isolated galaxies. Bias boosts clustering of massive halos, relative to the matter. Voids percolate, merging into bubbles with characteristic radii. Filament junctions funnel gas and set preferred satellite distances. Example in real terms, the local group spans about 1 megaparsec. The Virgo cluster sits 16 megaparsecs away, anchoring our region. The Boötes void stretches roughly 60 megaparsecs across, eerily sparse. Satellites around galaxies prefer specific radii, sculpted by tides. One-sentence recap, surroundings modulate the raw mass-driven scales. Maps show walls and filaments outlining huge, hollow basins between them. Galaxies inherit spins and alignments from this anisotropic web. Tidal torque theory explains why disks align with surrounding sheets. When tides are strong, only tight, dense satellites can last. When tides are weak, fragile dwarfs persist, drifting for eons. Net result, place matters, carving additional scales into the hierarchy. Your address in the web decides your cosmic neighborhood's size. That choice layers on top of the universal seeds we discussed. That hidden ruler still hides in galaxy maps, ticking across space. Pressure, gravity, and expansion chose the sizes we see. From microhalos to voids, each scale follows a simple rule. Now you know how the cosmos picks its blueprint. If that clicked, share this with a space-curious friend. Thanks for watching and keep looking up carefully.